Hey everyone, we are starting our second section of chapter 6. This section is all about transforming and combining random variables. By the end of this lesson, you should be able to describe the effect of performing a linear transformation on a random variable. You should also be able to combine random variables and calculate the resulting mean and standard deviation. And finally, you should be able to calculate and interpret probabilities involving combinations of normal random variables. A lot of the examples that I'm going to go through in this video are straight from the textbook, so feel free to follow along there. To save space, I didn't print them out, but know that they're in your book. There are some examples in these notes where they're not completely worked out, but the answer key is going to be posted on the class page, so look there if you want the full worked out version. So we're going to review a bit from chapter 2. This is information back from chapter 2 when we transformed data. We found that when we added or subtracted a constant, it would also add or subtract a value to the center and the location. So things like mean, median, quartiles, percentiles. It also is not going to change the shape of the distribution or the measures of spread. So the range, the IQR, the standard deviation, none of those are affected when you add or subtract a constant value. We've also seen that when you multiply or divide by a constant value, not only does it multiply or divide the measures of center, but it also does the same thing to the measures of spread by its absolute value. So that is just a review. It also does not change the shape. Now, the same thing is going to be true when you do this to a value of a random variable. So the difference between doing it to some value, like so data values, it's going to be the same as if you do it to the random variable, okay? It does the exact same thing either when you add or subtract or multiply and divide. Just a note down here, multiplying by a random variable by a constant b multiplies the variance by b squared. Because remember, the variance is just the square of the standard deviation. Standard deviation is the square root of the variance. So some linear transformations of random variables. If y is going to be some transformation, right? A plus b times x. If it's a linear transformation of the variable x, then the probability distribution of y is going to have the same shape as the probability distribution of x, right? We said no matter what you do, the shape stays the same. Now, to find the mean, right, you would have to both multiply and add to the first mean. And then to find the standard deviation, you would simply multiply the previous standard deviation by the absolute value of whatever it is you're multiplying by. So this works for both discrete and for continuous random variables. So here's an example. Pete's Jeep Taurus, and again, this is from your book. Pete's Jeep Taurus offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Define X as the number of passengers on a randomly selected day. So we have our different passenger values, right? 2, 3, 4. Remember, it has to be at least 2, so 2 or more. And then here's the probability that we would get that number of passengers on a randomly selected day. Here is a visual. It's a histogram of our probability distribution. So here's the distribution in table form. Here's the distribution in a visual form. You can see how we have the number of passengers and their probabilities here on the y-axis. If we wanted to calculate the mean of this random variable x, right? If we wanted to calculate the mean of the number of passengers on a randomly selected day, the expected value, you take each random variable value, x, times its corresponding probability. So you can see that here. And then you would sum those together, and we get an average of 3.75. If we wanted to find the standard deviation, first we have to start by finding the variance. Remember, you can do this in your calculator, but you will need to show at least the first couple and probably also the last one. I don't typically do that one, but you can, just to show whoever's gradient, whether it's me or an AP grader, that they know how to do the problem. And you get a variance of 1.1875, but you got to remember, we take the square root. And so the mean of x is going to be 3.75, and the standard deviation is 1.090. Okay. So what are we going to do with this? Well, Pete charges $150 per passenger. Okay, so the random variable C describes the amount that Pete collects on a random day. So obviously if it's 2 passengers, $300 3 passengers, 450. You see the idea. Now, you'll notice how it's the same probabilities as above, because if that's the probability you get that number of passengers, it's going to be the same probability that you get that amount of money. So we have, again, the distribution in a histogram form, right, of this discrete random variable C, the amount of money that he collects. Here's our formula to calculate the mean. Again, same idea. Our mean ends up being $562.50. Standard deviation, again, start by finding the variance. Take each value of C, subtracted by the mean that we just calculated, times its corresponding probability. Well, squared it and then times it. Add all those up, and then square root it. So we end up getting a mean of $562.50 and a standard deviation of $163.50. Okay, so if we're comparing these two, the shape of the two distributions is exactly the same shape, right? I'd say roughly symmetric. The center, the mean of the X for the number of passengers was 3.75, whereas the mean of the cost, C, was $562.50, which is just going to be the original mean times 150, because that's how much it was per ticket. The spread for X was 1.090. The standard deviation for C was 163.5, which is, again, just 150 times it. So you can visually see and also see from the calculations how that transformation works. All right, still considering Jeep and Pete's Jeep tours. So if C is, again, the amount of money, if it costs Pete $100 per trip to buy permits, gas, and a ferry pass, the random variable V is going to represent the profit that he makes on a randomly selected day. So if he was going to make $300, if he collected it, you have to take away 100 to figure out the actual profit. Now, if you went through the math, you would see that the mean of this guy is $462.50, and the standard deviation is $163.50. Now, if we wanted to compare, again, the shape, the center, and the spread, it's going to be the same shape no matter what, but now the center is subtracted by 100, but notice how the spreads, standard deviations, are the same. Standard deviation is not affected by adding or subtracting a value. Right, and we can see that graph there. The shapes are the same. I wouldn't even know that they were two different graphs unless I looked at my x-axis. Okay, so here's an example that I want you to try. In a large introductory statistics class, the distribution of x, which represents the raw scores on a test, was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and then adding 10. All right, so if x is the raw scores, we want y to be the scaled scores. And we want to find the mean and the standard deviation for this random variable y, and then find the probability that a randomly selected student has a scaled test score of at least 90. All right, so literally press pause and do this. Here are the short answers. Again, the long worked out answer is on our class page, so you should look there if you want to see the long detailed answer. Next example I want you to try. One brand of bathtub comes with a dial to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature X of the water follows a normal distribution with a mean of 32 degrees Celsius and a standard deviation of 2 degrees Celsius. Let's let Y be the temperature in degrees Fahrenheit. And in case you didn't remember from, I don't know, some science class, to convert from Celsius to Fahrenheit, you times your Celsius by 9/5, and then you add 32. So you're doing two things there. So let's find the mean and the standard deviation of our random variable y. And then let's find a probability. We want to know what's the probability that the water temp is going to be between 90 and 100, because that's the recommended temperature for a baby's bath water. Again, press pause, try this example. Here is the short answers of your final solutions. Again, if you want to see the worked out version, go on our class page and look there. Next video is going to be all about combining random variables, so stay tuned for that one.